Hey guys, how's everyone doing today? So I have a video that I'm making right now for the Beer-Lambert Law. It's the lab on pivot interactives. So I'm going to do my best to explain this for you, and hopefully it will all happen in one take, and I don't have to do multiple videos, but we'll see how it goes. So first of all, um, part one, measuring percent transmittance. The first section tells you how to use the Pivot Lab videos. So the Beer-Lambert law utilizes a cuvette, which is a small rectangular plastic container. It's going to have a solution in there. The solution is going to be colored depending on what the contents is, depending on what the elements are. And it's going to be placed in front of different colored LED lights. Okay. Um, so what's also important to know is look at this last bullet point. It explains that every video, the second half of the video removed the color and all you see is a gray scale. So if we didn't have the gray scale, we would have to look at the light. And if it was a red light, we would have to think, okay, is that red light really bright or is it dim? And it's hard to tell when it's just when it's a colored light. But when we take away the light and we make it grayscale, it's a lot easier to tell. So that's one of the perks of Pivot as opposed to doing it in a lab. With Pivot, we can make it a video, and they obviously already made the grayscale for us, so that can easily be determined. Let's just quickly watch this video that they gave. So if you look, there's blue solution and a red solution. And they identify the red to be the cobalt chloride, and the blue is the copper sulfate. That's very important to know. Different elements are going to give off different colors. If you remember the flame lab, you usually do the flame lab in sophomore year chemistry, whether it's an honors level or a standard level, you usually do a flame lab, and depending on the different substance, it's going to emit a different color when it's burned. The exact same thing is true when a substance is dissolved in water. If it has some sort of color, it will usually be revealed when it's dissolved. Another thing to keep in mind, the stronger color is usually the higher concentration. So that means the ones that have 0.0 molarity, that's basically just distilled water. But it's important to measure the absorbance of the distilled water, because then we can use that as a comparison to everything else. So as you can see, this is them putting the cuvette. It looks like they have the copper sulfate solution. It looks like it's the stronger concentration, and they're shining a different color light through it. So the different color light is going to read a different absorbance, okay? And there we see on top right there, that is on top is the actual LED lights, and then below is the grayscale. So they turned off, they got rid of the color, so then it's easier to measure using the grayscale. And we will be using the grayscale to measure our transmittance in the actual lab. Okay, so that video just showed what's going on. Now, when you reread through this, this is going to give us a chance to actually practice the measuring. So what is all this saying? This is telling us when we have our video that we can manipulate, we can change whichever substance we're looking at. For this lab and the instructions, it all gives copper sulfate. So we're going to be looking at copper sulfate. And some of you guys may notice on copper sulfate, it doesn't give a 0.5 molarity. That's okay. Using 0.4 would be a good thing to play around with because it's going to be the higher concentration, so it'll be easier to see the transmittance. So when we click load, we change the substance, we change the concentration, and then we can click load, and that will give us the correct video. When we click play, it's the LED light is shining through the cuvette. The lights are off, so all we see is the light that's revealed. We see the colored lights at the top, and then we see the grayscale at the bottom. If you look at these 4 selections there, you think of these are like rulers essentially that measure transmittance. They all have a different percentage, okay? The first one just goes from 1 to 100, so we can figure it out quickly. And the other ones give a more zoomed in version. This one's got 40 to 60, 60 to 80, and 80 to 100. So that is going to help us give more precise answers. And we can take this and bring it to the grayscale circle, and we can determine, okay, where do we think this is? You know, on this particular one, this blue light, it's actually pretty close to 90%, right? So what I would do is I would find the one that goes from 80 to 100, and I can see where exactly on 90% is it. On 92%, it looks a little too dark. So I'm going to say it's closer to 90, maybe 89-ish, maybe 88. Somewhere around there between 88 and 90. That's what I would say the transmittance is. So keep in mind, think about what I just put in there. I did the 0.4 molarity of the copper sulfate. The copper sulfate was a blue color. But even for the bluish, so the copper sulfate was a blue solution. But for the blue LED light, it has about a 90%, maybe 89% transmittance. That means 89% of the blue light is passing through the solution. That's the transmittance. That light is transmitting through the solution. Okay, so let's scroll down a little bit more. This basically, that's all this number 2 right here was asking us to do, to figure out how to use the tools. Number 3 is just explaining it a little bit more, and number 4 is asking you a question. The correct answer should be 45. So in this case, it was asking for a 0.5 molarity of the cobalt chloride. And the blue light is going to be the, when we do the blue light, it is going to have a 45 transmittance, 45% transmittance. Okay, scrolling down a little bit more. Now we're on part 2. So part 2 goes a little bit more in depth. We're going to start creating this table right here. So here's the thing, guys. You can be very customizable with these tables. I already filled this out. You may not have known that you should have done the LED wavelength in one end and the transmittance in the other. Maybe you weren't totally sure that's what you should be doing for this. That's okay. Let's look at what it's asking and try to determine how to make the table from what's being asked in the instructions. So the question here is, which wavelength of LED is most noticeably absorbed by each of the solutions? Let's just look at the copper sulfate solution because that's what it gives. So remember, copper sulfate is that blue solution. And I already kind of have it set up here. When it's at red, one other thing that you should know for this video, you can move this along. You can move this scale to get to where you need to get to. You can also move your, I'm clicking the arrows on my keyboard, right? If I move the arrows back and forth, I can get to exactly where I need to get to on my video. Okay. So which wavelength of LED is most noticeably absorbed by each of the solutions? What you want to do, I'm selecting my 0.5 molarity. I'm going to observe the color of that solution. But I want to go through each of the LED lights, okay? It says test red, yellow, green, blue. I tested each of the colors, and I want to point something out because and also the wavelengths. You may not know what the wavelengths are. That's okay. No big deal. You don't have to do any calculations with the wavelengths. I put those there so you know what the wavelengths are. That's a helpful thing to know. So, when we move back here, I'm at the blue. Okay, so this is what I did for you a little earlier. We're at 0.4 molarity copper sulfate. The blue light. The blue light, right, I'm matched up to 90%. When I'm at 95%, it's still a little too dark. But at 90%, it seems to match really well. And then I went a little bit further, and I think I decided that it was close to 89%. So I put 0.89 in the transmittance column. You could put 89 the percent. Later on, you might have to change something a little bit. I just put them in the decimal form of the percent. For this side, I typed in the name of the LED light, the name of the color. But take a look what I had to do. Click on these three dots. Column settings. Allow text data. If you don't click allow text data, it erased everything, first of all. But if I type in, it says must be a number, right? So I have to type in column settings and click allow text data, because right now we're not graphing anything. We're just making a chart to see a comparison. Okay, guys, so I typed in the wavelengths again, the colors of the wavelength, along with the numerical value of the wavelength. You didn't need to know that off the top of your head, okay? That's okay. I'm putting it there for your reference. So, take a look at what I wrote here. Blue has an 89% transmittance. That means 89% of the light passed through it, right? Cyan, 98% of the light passed through. That's interesting, right? So what that means is that the color of that solution is more close to the cyan color than it is to blue or green. And that makes sense because if you ever burn copper sulfate, going back to the flame test, if you were to burn copper sulfate, it actually has more of a bluish green color flame. So even though the solution from our eyes, it looks like a blue solution, it's closer to the cyan wavelength. I wanted to point that out in case you were doing this and you weren't sure of your answers. But what we really want to get to, and what is being asked, is what is most noticeably absorbed by each of the solutions. Look at red. The red only has a transmittance of 44%. And if I were to zoom, in the video, I'm gonna go close to the red light. There we go. The red light is right there. So if I take my, hold on one second, let me get closer. There we go. If I take my scale from 40 to 60, this is the best scale to use right now, and I'm matching this up, I would say 44%, maybe 45, but I feel like 44% really is the closest to the percent transmittance for red light. So let's think about this for a moment. Red light is being passed through a blue solution, and only 44% of that red light ends up fully passing through the solution. That means that that blue solution, or really it's a cyan solution, is absorbing like 56% of that red light. What we find out is that solutions absorb the opposite color. Colored solutions absorb their opposite color. I want to show you guys this color wheel right here. So this color wheel is specifically made for light. Do you see how there's no violet color? Because there technically can't be a violet LED light. That doesn't technically exist, okay? We have a magenta and we have cyan. Look at where cyan is, and we just determined that the color of our solution is probably close to cyan wavelength. The opposite of cyan is red. So that makes sense that it is going to absorb all of the red wavelengths and it's going to leave behind the cyan wavelength. That's why the color of the solution has that bluish tint to it. All right, so let's go back to this. Takeaway here, it is absorbing the red light the most at a 44% transmittance. So red light is what it's absorbing. That means the cobalt, if the cobalt is a pinkish red solution, that red solution is going to absorb the blue light the most. Which blue light? I'm not sure if it's the blue or the cyan, but it's going to absorb on that end of the spectrum more. All right, now let's get to the harder part, okay? So, part 3 is all about absorbance and concentration. What's nice about some of this, look at the equation for transmittance. You don't need to utilize that equation for this lab, which would be the intensity divided by the original intensity, okay? We could figure that out if we were, depending on what type of machine we were using and what we're calculating, but we don't have to do that equation for this lab. Basically, the transmittance rulers that they provided, the measurement tools in the video, already did that for us. So this percent transmittance, that's what we're measuring. We're measuring it using the tool they gave us. What we will have to do is this absorbance equals negative log transmittance. So I'm going to write another equation that you may have seen in the PowerPoint. So just hold on one moment. Okay, guys, so this equation, A equals 2 minus log percent T, that's the equation that was in the PowerPoint. The equation that Pivot is giving is A equals negative log of T. And I hope I said that right. This one, whoops, didn't mean to do that. Hold on. Didn't mean to do that either. Hold on one second. Hey guys, sorry about that. I didn't mean to erase that equation. So let me repeat one more time. The PowerPoint gives the equation absorbance A equals 2 minus the log of percent transmittance. Whereas pivot gives the equation A equals negative log of transmittance. This goes back to, are you using the percent, right? Are you doing 44% or are you doing 0.44? Either of these equations work, so you can choose either one you want to use. Totally fine. Just know that are you using the percent or are you using the decimal form. That's the only difference. Now I will erase that. Okay, so now this is the hard part. What are we measuring? How are we measuring it? And how do I figure this out? So first of all, the instructions, if we scroll down a little bit more, the instructions say to use copper sulfate, okay? If you used the cobalt solution, that's okay, it's not a big deal, but it asks for copper. I think it's not gonna matter, it doesn't matter. Just what I used was copper sulfate, so if you have different values, it's gonna be slightly different. Okay, so first of all, look at the concentrations. Under copper sulfate, these are all the concentrations that are given. We want to use all of them, okay? It doesn't matter in your data table if your data table is organized from highest to lowest or lowest to highest. That doesn't totally matter because once we plot it out, it'll plot it out for you in the correct order. But I happen to put mine from highest to lowest. So I happen to start my concentration at 0.4 and I just went all the way down to 0. I hope you guys understand how to do the measuring using the video. I think I kind of explained that earlier, so I'm not going to go through that again. But basically, I change my concentration. If I go to 0.5, I load it. I play, and I'm looking at only the red light. I only want to look at the red light for this one. And I'm comparing how the red light changes with each concentration. The reason I want to use the red light is because I'm using copper sulfate, and the red light had the most absorbance because it had the least percent transmittance, okay? So I'm using red light for copper sulfate. If I was using the cobalt solution, I would be using the blue light. So now I have to start putting my data in. I would first put all the concentrations in, and look what I typed in. I put concentration of copper sulfate right there. My units, I put M for molarity, capital M. Transmittance, note how I typed transmittance and not percent transmittance. And this is the part that takes a while, okay, to log each of those things, doing the concentration and then finding the correct scale, choosing the scale, and then measuring, looking at the grayscale. Okay, I'm at 44%. I'm going to type 0.44 here. And I do that for every single concentration. That just takes a while. It's tedious. The part that you may not have known how to do is to get the absorbance. We do have to do a calculation here. And what we're doing, I'm going to use the equation that was given in pivot, which is A equals negative log of T transmittance. I'm using that equation, but if you wanted to use the one in the PowerPoint, that's fine. So I could totally use my calculator and type in negative log of 0.44, and I would get that I would get this number right here, right? I would get this number if I type this in my calculator. Instead of typing it in your calculator, also, how did I get this column? If you click here, you can say insert column to the left, insert column to the right. And then over here, it can be insert row above or insert row below. What you can also do is click Change Column Formula. So once you've created another column, you click Change Column Formula, and you get this equation here. So you use this column formula tool instead of doing the calculation on your own every time. You can plug this in, and this will do the calculation for you. So in this right here, this gives you the name of every other column, okay? And if I wanted to, if I click C, I can clear it. So you can't really type in here. You have to type using these buttons, but negative for the negative log. I'm going to type log in, and then I'm going to plug in which column I'm using. I'm using the transmittance column. That's what I want to do a calculation for, and then I click end parentheses. And now it's good. I click submit, and that entire column will use the transmittance data, do a calculation to get your absorbance because I put the correct equation in. So let's look at a few things just at these columns, since I did put them in order from highest concentration to lowest concentration. One thing you'll know, the transmittance starts off low, and then it gets higher and higher and higher. That makes sense, right? Higher concentrations mean not as much light is passing through. So when the concentration is 0, I got a 0.99 transmittance. And that was my call as a scientist, right? You can make the call looking at your data. You may think, well, it's distilled water, it should have 100% transmittance. Maybe not. Maybe it looks like it's 99% transmittance. So you make that call as a scientist doing your own measurements. But the big trend here, transmittance increases as the concentration decreases. And look at the absorbance. The absorbance here, the thing about absorbance is not a percentage. These are not percentages, okay? This is its own number. It actually doesn't have a unit. So it's a unitless number. But it's at 0.35, then it goes to 0.34, 0.3, 0.2. So it's decreasing. The concentration decreases, the absorbance decreases. There's not as much stuff in there to absorb the light. Therefore, the transmittance increases. More of the light passes through because there's less stuff to absorb it. Okay, so you should have some sort of, depending on which you chose, either copper sulfate or the cobalt. Now, the transmittance, this is what you're measuring. These might vary a little bit. That's okay. I put 0.62. I put 0.61. You might think it's 0.62. That is your call as the scientist, as the person doing the lab. Now we get some sort of, but right now, if you didn't do this yet, you might have, everything might be blank, okay? When you click here, you got to click the column. I clicked concentration of copper. Don't worry about this uncertainty column. When you click here, you click the absorbance. You could click transmittance, but we really want to look at absorbance. So that's how you pick the column for each axis. And then here, you click curve fit, and you're going to click linear. You want to click linear right there. Now you're going to get a line. And look at this X right here. Do you see how there's an X right here? That means that the computer pivot determined that particular point to be an outlier. Okay, it basically said, you know what, that point doesn't really match the line at all. We're going to disregard that point. It is okay to have an outlier. It's totally fine to look at one piece of data and say, you know what, that doesn't fit the trend at all. There must have been something wrong with the measurement. There must have been something wrong. I'm going to cross that out. That is okay. And then we look at what the curve is. Now, keep in mind, if you have a lot of outliers, then there may be a bigger problem. But if you have 1 or 2 outliers, that's okay. So now we have this line. It's going to give you data for, or I should say, calculations. It's going to give you calculated values for your linear graph using y equals mx plus b. This a is not referring to absorbance. This a is referring to our this a is referring to the slope, the slope, the slope, the slope. This b is referring to the y-intercept. Look how small the y-intercept is, 0.01105. Your y-intercept should be really close to 0, okay? Sometimes if it's so close to 0, you can disregard it. RSME, ideally, we want this to be as close to 0 as possible. You might see somewhere r squared. Maybe you've seen r squared in Excel or Google Sheets. R squared is similar to RSME, but they're different. R squared, ooh, oh shoot, it's zooming in. Didn't intend for that. R squared is, you want it to be as close to 1 as possible, so it's usually like 0.9999. But RSME, I think you want it to be as close to 0. Here's the thing, you don't really have to worry about that, okay? But you will see that in higher level classes, so it's important to know. All right, let me fix my zoom just a moment. Okay, I think I got it back now. All right, display curve fit uncertainties. You don't have to do that. That basically tells us a certain error on the calculated values that they determined. We don't need to worry about that. But we do need to know what our values for our y, for our linear line. Sorry, equation for our linear line. All right. All of this here, that's basically what I went through with you. That's all the instructions that you needed to go through. All you need to put right here is what your equation is. So this is what I got. Y equals 0.9629 x. Y is my absorbance, x is my concentration, plus 0.01105. That would be, that is my equation, and that's what I am putting in this blank spot right there. Okay, so you put your equation right there. Now we have the mystery concentration. So, again, we want to stick with the substance that we were just doing. So copper sulfate, stick with copper sulfate if that's what you were using. And mystery solution 1, it kind of doesn't matter which one you choose, but in the instructions right here, it asks for mystery solution 1. So I already did it. I got it to be about 71%. Again, we're looking at the red light. The red light is right there. You know, you can take a guess at it where you think it is. I think it's somewhere between 60% and 80%. Let's match it up here. If I look, right, 79, that looks a little too dark, right? But if I look by 60, that looks a little too light. So let's get somewhere around there, 71, 70, somewhere around there. That's what I determined the percent transmittance to be. So use the equation, show your work below. This is what you would do on a separate sheet of paper and then load the image using this tool right here. It should pop up. So, you know, similar to homework assignments, you write something down on a separate sheet of paper, take a picture of it, email that picture to yourself, and then you can load in your work right there. What would my work look like? Well, let me show you. So, if I found my transmittance to be 0.71, that's my T, right? I can figure out my absorbance by using this equation. A equals negative log of T. So I would plug this in the calculator. 0.71, and let's see what I get. negative log. So you can't use your data from the graph yet. You have to do this first. So A, I got to be 0.149. 0.149. So I'm just going to put that over here. So if I have 0.149, now I need to use my equation. All right, I'm going to have to erase this for a moment. So now I have to use my equation, right? This was my equation right here. I'm just going to write it down on a sheet of paper so that I have it. Okay, so what did I determine my what did I determine my absorbance to be? It was 0.149. That was my absorbance. I'm going to use my equation, y equals 0.9629x plus 0.01105. And I'm plugging this number in for y. I'm going to plug that number in for y, and then I'm going to solve for x. I'm not going to show you that algebra. I'm just going to do it on my own right here. 0.01105 divided by slope. So if I solve for x, my x ends up being 0.14. Okay, that's my x. My x ends up being 0.14. What should that equal? That equals my molarity. Remember, x is my molarity. So look at these molarities that are given. What is 0.14 closest to? In this case, it's closest to 0.12. And that just so happens to be the answer, okay? 0.12. And then I think the first time I did this, I got 0.15. So once you do the, hold on just a second. Kind of a big difference there. So now you calculate the percent error. How do you do that? Percent error is always the experimental value minus whatever is the people call it different things. Depends what you were looking at. We'll call it theoretical. Experimental minus theoretical divided by the theoretical. Okay. That's going to be a certain percent. In this case, my experimental, what I calculated using my experimental data, I got 0.14. The theoretical, though, was 0.12. How do I know that? That's what was given in the answer right before. So what does that equal? It ends up equaling, if I round up, oops, sorry, that's a little weird. It ends up equaling about 17%. So I had 17% error. That's actually pretty high. It really is. Now, yeah, you are close. If you got 0.14 to be your answer, that does look to be pretty close to 0.12. Like, you did a good job. But in a highly calibrated lab, 17% error is kind of high. You probably want it to be lower. Okay, so that is my explanation of the Pivot Lab. This video is obviously a lot longer than I intended it to be, but I hope it was helpful to you. If you have, oh, there is one thing that I did want to bring up. Okay, so hold on for another minute or two while I explain something because I want to bring the PowerPoint in as well. All right. Let's look at the PowerPoint. So the other thing, it gave this equation. This equation here is what the equation of our graph is, okay? The slope are are these two values multiplied by each other. We don't, in the lab, we didn't have to do that. You may not have to really solve for this that often. I don't see it happening, but you may see this equation at some point. And so you need to know if you see a linear graph of absorbance versus concentration, if you see a linear graph, the slope of that graph equals the molar absorptivity constant multiplied by the length of the path of the light traveled by the light. And that's going to vary for every spectrometer that you use. So, sorry, I had a slight technological error there. As I was saying, the slope should be equal to the product of these two values here. If you see a line like this, we see a direct relationship between absorbance and concentration, which makes sense. If we have a higher concentration, there's going to be more stuff to absorb that light. And so these slides basically just explain what I was just saying, okay? If you guys have additional questions on Beer's Law, please let me know. I'd be more than happy to explain additional things to you. Hopefully this lab helped you out. Hopefully this video helped you out. So have a great night, guys. I'll see you later. Bye.